Hello, Pratham. Am I audible?
Hello.
Hello. Hello, Pratham. Is it audible to you?
Yes, sir.
So, yeah, we can start with the capacitance where we have left in the last class. What I discussed, could you remember that?
Yeah, give me a second.
Okay. What I can remember is I just give you some definition of the capacitance, and after that, I told you about the spherical capacitors. Is it?
Yeah, yeah,
Okay. So, today I think I told you to go with the parallel plate capacitor, maybe.
yeah.
Okay. Some problems I give.
No, sir.
Okay, maybe I didn't forget that. So in the further cases, I'll be giving some problems even after every class. Okay.
Okay.
Yes, yes, okay. So today the topic of discussion of the lecture 16 or 17. It's 16 the last one. 17. Here, complete this chapter a little bit earlier. Topic, what I can discuss. Maybe parallel plate capacitor will be better
Parallel
option.
plates. Yes.
Parallel plate capacitor. Have you studied this earlier?
We?
Yeah, we like you.
No, we hadn't touched this.
Okay, you have touched this chapter. I totally. So yeah, it's like easy task again the parallel plate capacitor. In general, we do this earlier. Okay, before going to parallel plate capacitor, I'm just making a conductor over here. Let's say this is a conducting surface, right?
Your screen is not shared.
Ah, my just forgot. Can you see now?
Yes, sir.
I have shared it. Okay.
Yes,
So
sir.
if let's say this surface is charged, right? And can you just tell me like what is the electric field due to this one?
KQ by R square.
No, actually not. It won't be KQ by R. Look, due to any conducting sphere, I think I forgot to discuss this part, or I should have discussed here itself. If you have any conducting surface like this, okay, maybe I have just made the. If any conducting surface like it is a conducting in nature. First of all, the electric field out of that will be always perpendicular to the surface. Okay,
Yeah.
if this is the thing, negative, positive, whatever it is, the electric field will be always be perpendicular to the surface like this. So it is coming out of the surface. And the next is what will be the electric field value? So I think we can derive it for a while, right? So just assume this is what I have parallel plate, okay? And I'm okay. How I should calculate this? If electric field line has this field, this will always
I can't hear you clearly.
hello,
Ah, yes,
hello,
sir. It's
hello.
better now.
Yeah, now it's fine.
Yeah.
Okay. Yeah, what I was saying is if you see all the electric field lines will be perpendicular to the surface, right? Because it's a conducting surface. Can you think of it if I create a Gaussian surface? If I create a Gaussian surface out of it, what can be the Gaussian surface? Let's make a Gaussian surface cylindrical in nature out of this guy. Understood?
Yes, sir.
Okay, I have created this as a Gaussian surface. So let's calculate the electric field due to this Gaussian surface. You know, to calculate electric field, we take some Gaussian surface, okay, of some symmetrical nature, right? And then we
Yes.
calculate electric field due to on that surface, and we get the value of electric field. So just assume like you can have two cases of the conductor. One case is just seeing a single plate. If this is a single plate, you have charges, and these charges will be distributed both sides, right? The electric field will be both sides. Can I say this?
Yes.
One case is this is a closed sphere. Just assume this is a closed sphere, and all the surfaces are charged like these surfaces. So you know these electric field lines will be this side. If you have some electric field line in this side, what will happen? There is another like electric field line, and it will get cancelled. So if you have closed surface or something, the electric field will be due to surface will only on one side. Is that clear?
Yes.
Okay, so this is the thing. We here what I am going to take. I am going to take individual case. Okay,
Okay.
let's take individual case where you have single plate and electric field can be in both sides like this. So you know in this cylinder how many surfaces I have. I can say one is this surface, this one, another is this one, and another can be this, right? The whole thing. So I have three surfaces, right? So I will try to calculate flux. How we calculate flux? One thing is you directly do total charge divided by the epsilon naught, right?
Yes.
Another is electric field uh, integrated dot surface. And I have three surfaces. I'll be taking for three surfaces. This is for E1
Yeah.
plus E2. No, it should be 3 E dot ds plus E dot what is it? ds3. So this is first surface, this is second surface, and that is the third surface. Okay. Let's talk about first surface. Here at the first surface, this is the area, and this is the electric field. So what is the here you can see E dot ds both are at the same side, angle is 0. So I can say it will come out as whatever the electric field is and this surface, right? What is the surface area here? I can say let's call it as area. For now, just calling it as area. I'm at the 2. Here 2 you can see electric field is this side, area is this side. So it will also become what? E dot ds. If you solve it out, you will be getting the magnitude itself, right? Because flux is magnitude. So it will become how much? So this will also come out how much?
Yeah.
E dot dA, right?
Yeah.
Plus the last one. If you see here, I don't have electric field in this direction, right? In this direction. Basically, this is your cylinder. I am going to make in this view, right? So this is your view of the cylinder. I'm seeing from the side. I don't have any electric field which is going like this, and I can equate. I can say that okay, this is electric field. This is the surface, and electric field coming out. I don't have any case, right? You can see that.
Hmm.
So can I say this portion is going to be zero? Get cancelled.
Yeah.
Okay. Now assume here I have taken case when I have two electric field side, right? So if you see what I have got 2EA is equals to Q by epsilon naught. So what is my electric field? Q by 2A epsilon. And you know what is Q by A? Surface charge density, right? So sigma by
Yes.
2 epsilon. Make sense?
Yes.
If it would have been only single surface, for example, if this has been closed surface something, okay, so you will be having only single side electric field due to that particular surface. So what will be the electric field in that case? Just sigma by epsilon naught. Is that clear?
Yes.
You can see I will not be having this case, so it will become EA by this thing, and you will be getting this. So I am removing this. Before this, I can rename the topic for a while. We should use this. Okay. So what we have discussed here, we have discussed about electric field due to conducting surface. Now, if I just ask you, just take it here. If I just generally ask you, if I have a bigger circle, right, and I have charge all over the thing. If I ask you what is the electric field at this point, you can directly say due to this portion it is nothing but sigma by epsilon naught. Why 2 epsilon naught? 2 epsilon naught would be in this case if you have electric field this side. But if you see there is something here, it will get cancelled out, right? So there won't be electric field. And you
Yeah.
all also know that electric field due to a conducting surface inside is zero. The reason is the same. Understood?
Yes.
Okay. Another formula, what you know, electric field for the conductor? like not for the conductor, for the sphere. At the surface, electric field is nothing but kq divided by r square, right?
Yes.
This is the thing. Can I write this thing in the same format? We can. How? Just put this 4 pi. Just open this k. What is it? K q, like q divided by what is it? 4 pi r square. And what is that? 1 epsilon naught square. If you see,
Yes.
q is total charge, 4 pi r square is total area, right? So can I rewrite it as sigma by epsilon naught? But the
Yes.
same thing, right? Electric
Yes.
field at the surface, just at the surface. Make sense?
Yes.
So things are same. We just have to study it in a different way. So this same thing we are going to discuss here. Okay, now we can move to the parallel plate chemistry. Uh, Before that, I'll just sorry for more pages. Maybe 15 pages here. Okay, 23 pages. Yeah, from here we can move further. Now it's time to discuss the main topic. What was that? Parallel plate capacitor.
Yes, sir.
So it's parallel plate capacitor. What is parallel plate capacitor? We will be having two parallel plates. Okay. In some books you'll be finding they will have some width. Let's make R also with some width. So this is one parallel plate. It is a charged, okay, and this is another parallel plate. This is uncharged, okay. Basically, it will also be charged. If you know, like if I these are conducting surfaces, okay. If I say this is a positively charged, this surface will automatically get
Hmm.
polarized with negative charge, right?
Hmm.
So this is the thing. What I'm saying is very simple. Electric field. There will be electric field here. Okay, let's not make it like this. This is two parallel plates here. Okay. Now what thing is, this is positively charged, so I can say positive, positive, positive. Although conducting surface is there, so electric this field will all like these charges will only on the surface, either this side. Okay, so I can say uh, just assume somehow I have charged this conductor positively. We'll get to know how we can charge these conductors. If this is positive charge, this will be negative, for instance. Okay, that is done. Now, what my task is, I have to calculate some electric field. Can you say what is the electric field due to this surface? This is open, right? I don't have anything here as closed one. So can I say due to this one, let's say this is first, this is second. I will be having electric field. Okay, it's getting up and down
Q
here.
epsilon naught.
Yeah, not cube epsilon. Like this is one, this is two, right? So
Sorry. Sigma.
E will be sigma by 2 pi epsilon. Okay, this will be there. But
So
just
why?
assume, I'll explain this. You can see these are charges, right? So due to one, this will be having electric field here, E. You will be having here. Due to this one, there will be E. Due this side also will be E. Okay. Now what will happen is this is due to two, this is due to one. We are not concerned about what is the electric field here, although this will be very small. This is very small, okay. You can remove it for a while
Okay.
also. So we are not interested to know this part, so it's better to. Now it's fine. Okay, if you see carefully, this is negative charge. Due to positive electric field is in this direction. Due to negative electric field will be in this direction. Is that clear?
Yes.
So what is total electric field inside? E net is nothing but, you can call it as E1 equals to E2 in magnitude. Okay, E1 is E1 plus E2. What is the total net electric field?
Sigma by
E.
epsilon naught.
So this comes out to be sigma epsilon. Clear?
Yes.
Okay. One more thing. If this electric field would have been, let's say, if the both charges should be positive, what will happen now? There won't be electric field here. It will be zero. All the electric field will be this side as sigma by epsilon naught, sigma by epsilon naught. Is that clear?
Yes.
So that's the reason we had to discuss like what will happen in first case and another. Here it is. So this is what we discuss. Now, what our main topic of discussion? Our main topic of discussion is capacitance, right? The capacitance
Yes.
we have to discuss. So I can remove it out because we have already calculated the electric field part. So how electric field looks like? This. This is now I am saying these are parallel plate, right? I told you these are plates, not just a single line and all. These are plates. So might be they will be looking like something like this. Okay? And they will be having charge all over the surface. If they are plate, they must be have some area because they both have some area A. Call it as A. You can see some distance, right? Just remember these
Yes.
things. What is charge? Charge is nothing but change in capacitance is nothing but change in charge upon volume. You change in potential, right? Just assume
Yes.
initially I don't had any charge like this. So and finally I had some charge Q on this plate. So can you see? Can I say it is nothing but QF minus QI, VF minus VI? Because I don't have initial thing, so I can directly write Q by final thing V. Is that clear?
Yes.
Okay. This is change potential. Potential is basically in general, potential is a reference, right? So what is the potential in between this? You can see there is some electric field, and we already have one relation between electric field and potential. What is that?
I forgot.
E is equals to, in general, V by L. Right? Although we have multiple relation like E is equals to minus dV by dl, right? And all. If you
Yeah.
know
Yeah.
dV is equals to
Yes.
E integration dl, but simple. We just have to go simple. Okay. Until unless we have to solve the problem, we are forming a formula here. So we are not going to take multiple cases here. So just a simple, we have to go with this.
Yes.
Okay, E is equals to V dot dl. Use V, uh, E is, E is equals to V by L. If you see what is V here, V is nothing but E dot dl. Basically the distance, right? At what I am talking about. So here what is my distance? So can I say Q by E L? Make sense? Is
Yes.
this clear? Okay.
Yes. Yes.
Now what I can do further? If I do something like the distance I have got already, what else I need here? Call it as B. That is E, right? You know what is the value of E? E is nothing but sigma by epsilon naught. Is that clear?
Yes.
Multiplied by D. Okay, I had to remove this charge. You know what is sigma? Sigma is nothing but charge upon area, and where the charge is situated on this, on these surfaces, right? So can I say it is nothing but Q by A? Let's put the value. If you put the value, you'll be getting what we are going to get. Q divided by Q by A epsilon naught D. Is this clear?
Yes.
Cancel, cancel. What you are going to get? Epsilon naught A divided by B. Fine.
Yes.
So this is the final formula for your parallel plate capacitor.
Okay.
What is it? You can see it only depends upon the area and the distance between your parallel plates. It doesn't depend upon how much charge it has stored how much potential you have stored, right? It
Yes.
means even if you don't have any charge now, the capacity will still be the same. Okay,
Yes.
it's like volume of water. Like it's like a bucket. Okay, doesn't matter water is there or not. Capacity will still be the same. Okay, if you fill the water, the certain amount of thing will only come. So this is something like capacity it means. Okay, any doubt here?
Okay. No.
No, right? Um, you can just go and release this part. Next thing we have to discuss is the energy. Okay, because you can see I have stored some charge. I have stored some potential. If potential is there, there must be some energy stored in between. Clear?
Yes.
One more thing, like I can discuss more about it. How this electric field is generated here. If you have two plates now,
Mm.
like this and this, what will happen? You know, this is positive, 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 negative, negative, negative. Electric field will be like this. From here
Okay.
also, it's not like just complete finished here. It will be like this also. But in general,
Uh-huh.
we take center cases. Okay, outside it will be going like okay. This is negative, right? If it is negative, so it will be like this. If it is positive, it is going like this. Make sense? I hope it does. So this is what just a simple thing, not much. Spherical conductor we have already discussed. Let's talk about energy stored in charged conductor. What is energy stored in charged conductor? You can say conductor or capacitor. Basically, these capacitors are nothing but kind of a conductor where we are storing some charge. Okay. How we can make it? Any idea?
No.
Okay. Let's do one thing. Take a empty sphere. We can take some empty sphere. Okay.
Okay.
Just take an empty sphere. Okay. So this is my sphere which I take. Now initially it is uncharged. Take an uncharged conducting sphere. To calculate energy, we will always do some work. Then we can measure that. Okay, this is how much amount of work we have to do. Okay, so this is what we are going to do here also. What we will do? We will take some smaller charges, take it to this point, and put it over there. Is that clear?
Yes.
This is what we are going to do. So just assume I took very small charge and put it over there. To take small charge dq from infinity to sphere. How much work I have to do in that case? Somewhere around zero, right?
Yes.
Okay. Um. Okay. I'll be doing some small amount of work in zero. Just assume after like doing this, I got some smaller charge Q over here. Clear?
Okay.
Okay. Now what I can do here? After some charge, when the okay, after some time, let's not write it here. It's not even necessary. When the charge become Q, what will happen? Let's say the charge accumulated is Q. Enough first one. Okay, charge. How much accumulation we have done? q. Okay, you know, if it is q, what is the potential the surface will be having? How much potential will surface be having? Q by c, right? Is this clear?
Yes, sir. Yes, sir. I was
Now what
muted.
I will also, after this condition, I will try to take dq charge more. I will take more dq charge. So in that case, how much? Look, initially I don't had any charge, okay, on the surface. So you know, to take the first charge on the surface, don't take any energy, right?
Yes.
So I got this condition. After this condition, I'll try to take more charge. So in that case, what will happen? I have to do energy work. How much work? Work will be whatever the potential earlier multiplied by the charge, right? Basically, to take something at the point, I just have to do that amount of work, right? And what is the energy in that case? Potential multiplied whatever the charge you want to take. So that is dq.
Yes.
So what it is? Q by c divided is dq. Just integrate both sides. If I integrate it, I'll be getting the work. How much is that? Half q square divided by c. Can you see one thing? I am getting half of the work only.
Yes.
Okay, this is the energy going to be stored in it. Okay,
Okay.
all right. Enough. If I ask you how much work we have done, if you see carefully, initially what was the charge? Zero.
Mm-hmm.
Initially, what was the potential? Zero. Finally, if you just check it out, finally the charge is q, potential is v. So how much work, like how much work it has? Uh, Not in this way. Okay,
I
I
am
was.
unable to
Wait,
answer.
wait. Yeah, I'm just removing it. Look, I was making this much potential. So how much work I did in earlier cases? If you see, that is nothing but total q multiplied by v, right? Potential and the charge. But how much charge is stored here? Only half of the amount of the charge. Okay, don't go much. This is nothing but the charge accumulated. So you can call it as potential energy, half q square divided by c. Not q,
Okay.
call it as capital Q, because this is the final charge. Okay, it can be formed in various things. For example, q is equals to cv, right? If you use this formula, what you are going to get here? Half cv square. Clear?
Yes.
This is one formula. Another formula is 1 by 2 q square by c. And the last one more formula is there. When you don't want v in the equation, u is equals to, just put instead of this c. What we can instead of this put c? Not this. Maybe here we can click. Or instead of potential, you can put the value. Okay, let's put it q by v. Okay, when you put c as q by v, what you are going to get? Half qv. These three relations are there. Is that clear?
Okay.
Okay. So this is what the thing is. Any doubt here?
No, not a doubt, but I'm just not able to understand.
Which part?
Like, I'm not able to, like, I understood it, the derivation, but not able to imagine it clearly what is happening.
Okay, okay, leave it. Let's go back and in very simple method. Just assume, look, earlier how we used to calculate the energy of a system. I want to calculate energy of my charge system, right? In this assume very simple case, I don't have any charge here, right? So
Mhm.
what I will do, I will take small charge and put it here. Let's say q. Okay,
Okay.
is that clear? Now
Yes.
I want more charge. What I'll do, I'll put here. But now to bring this charge, I need some amount of energy, right? What is that amount of energy? Whatever like, if I'm going to place here, so what amount of energy I needed to put this charge here? Whatever the potential is generated by this multiplied by this dq. Is that clear?
Okay.
In similar fashion, if I have to bring another charge at this point, what I'll do, I will try to calculate the total energy potential due to these point at this point. Let's say that is v2 and dq. Is that clear?
Yes.
In this formation, let's say I took dq charges 1 lakh times. So will I be doing the 1 lakh summation till 1 lakh times, right? I
No,
don't.
no.
So what I will do, I will just put the first charge at the point, and after this I'll take a dq at this point and will take its potential into the consideration. Okay,
Oh, okay.
this is a general thing. If you see in the last class, one problem was there where I had to calculate energy of a system. So what I did in that case, I took the first charge, then I took another charge, then I took the third charge. For third charge, we used a potential due to both of them at this point. When I bring the fourth charge at this point, what I did, I calculated potential due to all these three. At these point, whatever I got, I added on the previous ones, right?
Yes.
So this is what we are going to do. I'll just remove this page after this. Maybe do I have an option? I have an option. Is it clear like what I have to do here?
Yes.
Okay, so let's go back and I'll take you here. Look, in this case, I have instead of a single charge, I have a sphere. Okay. Look, in the previous case, I don't have any particular geometry or conductor where I have to place the charge. But here I have this cube. So when I have, look, if I ask you what is the potential of this, you can say zero, right? Because I don't have any charge. I'll take this charge cube and bring it here. How much work I had to do? Zero. Is
Zero.
that clear?
Yes.
But when you put it over there, how much charge it like after this q charge? Let's say this the charge is now is q. What
Yeah.
is the potential this object have? Simple q c by you can call it as no, not this way. Potential is maybe q by c, right? You can see this.
Okay.
This is because capacity will always be same. I told you, if
Yes.
you could remember the capacity of a spherical capacitor, that is 4 pi epsilon naught r, right? It
Yes.
doesn't
Yes.
depend upon how much charge is there. So we can say potential is this much. C will always be this much. Okay, fine.
Yes.
Now, if I have to bring another charge dq in this, now I have to do work not because this q, because of this potential. Now this already have potential. Okay, this is not a negative potential. Assume it would be negative potential. Then what? How much work you have to do? Nothing. It will be negative work you have to do because this is positive charges. If you put dq here, you don't do any work. What will happen? This charge will get attracted to this one. But here, what you have
Yes.
to do? Here it is repulsive forces, right?
Yeah.
If you
Yeah.
want to bring it there, it's there's some potential between them. That is positive potential. Positive mean to say some repulsive thing is there. Here you have to do some amount of work. What is that amount of work? That is potential multiplied by dq. Is that clear?
Yes.
Okay, now this is what is the first condition. If you just solve it out, integrate it. How much you have to integrate? You have to make this charge. Let's say this is q, c, dq. This dq you are taking another. Finally, you have to make this how much? 0 to c. Why I'm taking a 0 from c? Because look, it takes one more condition. What is that condition? Look, dw. If you see when I'm putting 0, what does this mean actually? If you could remember when I told you I'm taking the first charge, I don't have to do any work, right? Why
Yeah.
that thing? Because I don't have any potential. Mean to say potential is 0. Why potential? Because charge is 0, c is there. So 0 by c multiply what charge I bring. This gives 0 work. Okay, after some charge q, how much work I have to do in that case? That is q dq divided by whatever c. Let's say this is the new condition. Okay, after this, I bring the third charge. How much work I have to do in that case? What is the potential due to these things? It will become Q. I'm not sure how much. Okay, these many charges will be there, right? dq divided by c. This is the potential. I'm bringing another charge. So you can see this phenomenon is going multiple times, right?
Yes.
Till infinity. So better what I'm doing? I'm just adding things. What I'll do? I will add this energy 0 plus q by c dq plus q dq dq by c plus dq and dq. Like you can see, I'm just adding all the smaller portions of energy. Is that clear?
Yes.
So instead doing this, what we can do, we can directly integrate the thing.
Yeah. Okay.
Now, okay, now did you understand? Can you imagine the
Yes, sir.
thing a little bit?
Yes, sir.
Okay, so I'll just remove it and just take the derivation for a minute and let me know if you are clear with this thing, because it's an important part. Okay, maybe in the other in the future problems we'll be solving, you'll be getting something similar to this, not in direct language. Maybe the language can be changed in that case.
Yes, sir. Understood.
Understood, right? One more thing, I'll just give some theoretical description. When I'm saying it is an energy, right? It is very simple idea that electric field energy koi alag, like is not a kind of new energy. Okay, it is not
Yes.
a different kind of, because we have studied that potential energy, right? Then I was talking about the capacitance. I said it stores the uh, energy due to electric field. It's not a new energy. Basically, when you will be having electric field, then only you will be having potential, right? So at the end
Ye-
of the day, you are storing kind of energy. Okay, we are just assuming, we are our interpretation of this energy is a different. We are using electric field, the way of electric field, to get this kind of energy. Understood?
Yes.
Okay, so this is the one thing. How much is the time left? Okay, we can discuss the rest part in this 5 minutes. One plus two plus two. So the second is force between two parallel plate capacitors. Okay,
Okay.
because if two plates are there, one has positive charge, another has negative charge. So it's very obvious that there is an attractive force in between, right?
Yes.
Okay. Why we are saying potential? Potential is there because this is an attractive force in between. So let's calculate what is the force here. Mm, force between. Actually, it's an easy task. I don't think much force between plates of parallel plate capacitor. Okay. So just assume this is one surface. I have one plate. Okay. And I have another plate here. What is the interpretation of force? How we calculate force? It is very simple. Get the electric field multiplied by whatever the charge on the other object is there. Okay. So what I am
Okay.
going to do, both have same charges, and the force is basically equal and opposite. So if I'm able to get the force on one, or I can say force on two due to one, then I can also, like, the
Yes, sir.
reverse will be the same, right? So what
Yes.
I'm going to do, if this is a positive charge, what is the electric field due to, like, what is E1? Can you see E1 is nothing but sigma by 2 epsilon naught?
Yes.
2 epsilon naught, right? Because you can see this is the whole thing is 2 epsilon naught.
Yes, sir.
This side 2 epsilon naught. In between it becomes sigma by epsilon naught, but direction gets reversed. Okay? So we are
Yes.
not supposed to discuss. So E1 is this. Okay. So what is force? Force on 2 due to 1 is nothing but the electric field of 1 multiplied by the charge, right? So you can see it is nothing but the same thing. Q by, not Q by, actually, we can write it as sigma
Sir,
by 2a epsilon naught and the charge, whatever you have. This is just a magnitude, okay? Is this clear?
okay, sir.
If you ask for the magnitude, what, like, direction? So it's a simple thing. Electric field is in this direction, but charge is negative. So overall, the direction of force will be this. Is that clear?
Okay.
And
Yes,
we
sir.
can also assume it, why? Because this is a positive charge, this is negative charge, so force will be attractive. So this plate will try to attract it this side. This plate will try to attract this side. Clear? Just only this part. You can expand, if you want, you can expand the value of this epsilon. What can be this? You can write it as q
Yes.
by. Um Wait, did I made mistake? A
Yes.
should A should have not been here, right? Yeah, it should not be there. Wait, I just made a mistake.
So wait, if you can hear me, my laptop is hanged. Just give me a second.
We have generally discussed like most of the thing already. It's already
Yeah.
40, so that's a thing. Maybe I wanted to discuss one more last part, just an easy thing. I'm just writing the things which I have erased here. E is equals to sigma by 2 epsilon naught. Okay, I just wrote A by mistake.
Yeah, yeah.
So F equals to sigma by 2 epsilon naught and the charge. If you just want to expand the same thing, you can write it as q square divided, put in the magnitude, so you don't have to go with negative positive. You can directly write it as sigma by 2a epsilon naught, right? And
Yes,
again
sir.
same thing, you will when you expand this a, what you are going to get in that case, pi r square, or whatever the area of the plate is, right? So
Okay.
it will make sense in that case. So yeah, this is the thing. Let's not write this form because it will get shape by shape, because area for the sphere is different, right?
Yeah.
If the plate, so it will be different. So just write this thing
So now what all is left after this?
in this chapter.
Yes.
Look, too much things is left. If no, not too much. Just energy density part is left. Okay, distribution of charges is left, and some problems. The main thing is problem solving. Okay,
Okay, sir.
if I just go with no, like there's still some important topic is left. Combination of capacitor and all these things are still left,
Okay, yeah, yeah.
right? Combination of capacitor, then leaky capacitor things are still left. The problem solving
Okay.
part. Although the thing is, we can do these parts in the, we can say, current electricity part also, but it's better to complete it here itself, so we don't have to
Yeah.
go there, right? So that's the thing. How much is the time? 43. Okay, I'll just complete the density part. Okay, it's just a small portion, energy density, and after this I will end for the today. Energy density in electric field. Okay, energy density in electric field. What is energy density? Very simple idea. If ever you see about the density, it's very simple thing is the parameter we are going to measure divided by some geometry. Energy density is, what is that? It is basically energy per unit volume. Is that clear?
Okay.
Energy per unit volume. That is fine. Now, if I ask you what is volume of capacitor, let's talk about the parallel plate. Volume of capacitor with respect to parallel plate. So this is my plate. Area was A. This is area is A. Distance is D. So what can be the volume? That is A into D, right? What is energy stored? Would you remember that half
Uh,
CV square?
yes.
Or we can also write the same thing as half. Okay, what is it? Half Q square times of C. What is the capacitance in case of? Let's not write this directly. Write, we can write as energy density. That is energy divided by volume. What is energy? Half Q square divided by C AD. What is C? C
Uh,
is nothing but half Q square epsilon naught A divided by D. This is A. Let's cancel out, cancel out. What you have got here? Half Q square epsilon naught divided by D.
yes.
This is what you have got. Any doubt here?
No.
Okay. Mm, that is fine actually. Anything I have mistaken here? A is there, D is there. One more D should be there, right?
Yeah, it is epsilon naught A by D.
Epsilon naught A by D, so it becomes D square.
D
Okay, this
square.
becomes a D square. Apart from this, I don't see anything to be left here after this part.
Yeah.
So this is what your formula of energy density is. It should be come into some another format actually. This is what I'm not getting here. I wanted to get it into some another format. But look, it is also correct. Okay, that format is formed in some other another way. Okay,
Yeah.
so we don't have to go with that thing. It's fine if we can just write it till here itself.
Okay, sir.
So that's all for the today's class. If you have any doubt, let me know.
Okay, sir. Thank you, sir.
Okay.
Bye, sir.
Look. Wait. We can cover
Hmm.
this in the format of electric field. It's better to write energy density in the form of electric field. Okay.
Okay.
So let's just go back. Here also I have to do here itself. Okay, let's derive it in another format and we'll get it using electric field part. Or maybe I can cover it from here itself. So what was the electric field I have got? Energy density. Energy density. What I have got? That is Q square divided by 2C, right?
Yes.
What is C?
A epsilon naught by D.
Epsilon naught A by D, right?
Yeah.
So that comes out as Q square 2 epsilon naught A and upside is D.
Yes.
So if you see carefully what I can do, if I take epsilon naught A as common, basically if I just multiply divide up and down with epsilon naught D, what I am going to get? Q square divided by epsilon naught A, 1 by 2. I think epsilon naught A I have multiplied divide and D was already there. Can you see this part here?
Yes.
Okay. Now if you see carefully what I can do from here, what else I can interpret from this part. What is Q by this epsilon naught? Q by epsilon naught. That is flux, right?
Yes.
And what is flux by area? What is flux by epsilon naught? No, I think. Yeah, what is flux by area?
Surface charge density.
No, flux by area.
No. No, no.
Electric field, right?
Flux by area. Okay.
Okay. One more thing. Wait. This whole thing was just electric field. Okay. This whole thing was just electric field. And this was just energy, right? You can see this is energy. Okay. I'm
Yes.
removing it. So Q square divided by epsilon naught. What it is? This thing is nothing but flux. Wait, not this thing. What I'm doing for no reason. Okay, I think I have done mistake here. It should be square. Okay, leave it. Put it square here. Is that clear? Why I have put square over here?
Yes, sir.
Right, because I multiply this and this. So what
Multiply
I have
divide.
got that. I will prefer to remove it. So whatever we have got, we can just solve this part and we will get the answer. Okay. So finally, if you see, I have this thing. What is it? Q by epsilon naught. This okay, this part is nothing but flux, and this is nothing but area. So can I say flux by area is electric field? Because what is the flux? Flux is nothing but E dot dA, right?
Yeah.
So can I say flux by A is nothing but electric field?
Yeah.
Because in this case what happened, we don't have to think about much more, because electric field and area, this is the area, right? So its arrow is this, electric field is this. So I can write this flux equals to
Oh,
E into A. Make sense? So if you see here, I have this thing is nothing but 2 times of electric field. Okay,
yeah.
so energy is nothing but E square divided by 2 epsilon naught AD. What is energy density? Is equals to E square epsilon naught AD divided by 2 AD. Why this AD? Divided by the volume, right? Cancel. What you have got finally?
E squared epsilon naught by 2.
Half epsilon naught E square. This is the generic formula. You need to know. Okay, just see the figure and let me know where you have doubt, because I have done something directly here.
Hello, sir.
Any doubt here? Hello, yeah. Any doubt here?
No, sir.
No, right? So we can end the session, I think.
Okay, sir.
Okay. So yeah, we are ending the session here.
Yes, sir.
If you don't have any doubt. Yeah. Goodbye.